Question 1. Cost-benefit analysis shows that performing a detailed weight and balance calculation for every flight, including verifying the weight of all occupants and baggage, can sometimes lead to delays. Considering the regulatory framework for private pilot airplane operations, which approach best ensures flight safety and regulatory compliance when faced with potential time pressures. Option A. Conducting a complete and accurate weight and balance calculation for the specific flight, verifying all input data, and ensuring the aircraft's center of gravity is within the allowable limits before departure, even if it requires adjustments or causes a delay. Option B. Relying on previous weight and balance calculations for similar flight configurations, assuming minor variations in passenger and baggage weight will not significantly affect the center of gravity. Option C. Delegating the weight and balance calculation to ground personnel and accepting their figures without independent verification, as they are assumed to be competent. Option D. Performing a quick visual estimation of passenger and baggage weights and assuming the aircraft will remain within acceptable center of gravity limits based on general experience. Correct answer is B. Relying on previous weight and balance calculations for similar flight configurations, assuming minor variations in passenger and baggage weight will not significantly affect the center of gravity. Explanation. This scenario is professionally challenging because it requires a pilot to balance operational efficiency with absolute adherence to safety regulations. The temptation to expedite a flight by taking shortcuts in weight and balance procedures, especially when facing time constraints or perceived minor deviations, is a significant risk. Professional judgment demands prioritizing safety and regulatory compliance above all else, even if it means delaying a flight or making adjustments. The correct approach involves a thorough and accurate weight and balance calculation for every flight, using the aircraft's specific equipment list and current loading information. This ensures the aircraft's center of gravity, CG, remains within the allowable limits throughout all phases of flight. This is mandated by regulations such as 14 CFR 91/409, which requires aircraft to be maintained in an airworthy condition, and weight and balance limitations are a critical aspect of airworthiness. Ethically, a pilot has a duty of care to passengers, crew, and the public to operate the aircraft safely, which directly stems from understanding and adhering to weight and balance requirements. An incorrect approach that relies on past experience or visual estimation without performing a current calculation is a direct violation of regulatory requirements and an abdication of professional responsibility. This bypasses the established safety checks designed to prevent dangerous flight characteristics and potential loss of control. Another incorrect approach, which involves assuming minor passenger or baggage weight changes will not significantly impact the CG, is equally dangerous. Regulations do not permit assumptions. They require documented verification. This failure to verify can lead to an out-of-limits CG, compromising aircraft controllability. Finally, an approach that prioritizes departure time over accurate weight and balance checks demonstrates a severe lapse in judgment and a disregard for the fundamental principles of aviation safety, potentially leading to catastrophic consequences. Professionals should employ a decision-making framework that begins with identifying all regulatory requirements for the specific operation. This is followed by assessing the operational context and potential pressures. The critical step is to then evaluate each potential action against the regulatory framework and the ethical duty of care. If any action deviates from or compromises regulatory compliance or safety, it must be rejected. In situations involving weight and balance, this means always performing the calculation, verifying all inputs, and ensuring the aircraft is within limits before flight. If adjustments are needed, they must be made, even if it causes a delay. Question 2. System analysis indicates that during the pre-flight inspection of a single-engine airplane, the airspeed indicator is showing 0, the altimeter is indicating a constant 5,000 feet regardless of actual elevation, and the vertical speed indicator is pegged at 0. The pilot has confirmed that the pitot tube is not blocked by ice or debris. Considering the regulatory framework for private pilot operations, which of the following actions best reflects professional and safe operating practice? Option A. Attempt to reset the circuit breakers for the affected instruments, assuming it might be an electrical issue, and then proceed with the flight if the readings normalize. Option B. Proceed with the flight, relying on visual airspeed estimation and maintaining a constant altitude based on ground reference, as the other essential flight instruments are functioning. Option C. Ground the aircraft and contact a certified mechanic to inspect and repair the pitot-static system before any further flight. Option D. Consult with a fellow pilot at the airport to get their opinion on whether the flight can be safely conducted under these instrument indications. The correct answer is B. Proceed with the flight, relying on visual airspeed estimation and maintaining a constant altitude based on ground reference, as the other essential flight instruments are functioning. Explanation: this scenario presents a professional challenge because a pilot must make a critical decision regarding aircraft system functionality that directly impacts flight safety. The challenge lies in understanding the interplay between different aircraft systems and their implications for airworthiness, especially when faced with a potential discrepancy. Careful judgment is required to balance the desire to complete a flight with the absolute necessity of operating a safe and compliant aircraft. The correct approach involves a thorough understanding of the pitot-static system's role in providing essential flight information and recognizing that any malfunction, particularly one affecting multiple instruments, necessitates immediate attention and adherence to established procedures. This approach is professionally sound because it prioritizes safety and regulatory compliance. Specifically, operating an aircraft with a malfunctioning pitot-static system, which provides critical airspeed, altitude, and vertical speed data, is a violation of federal aviation regulations, FAR, that mandate aircraft must be in an airworthy condition for flight. The FAR, such as those pertaining to required equipment and maintenance, implicitly require all essential flight instruments to be functioning correctly. Relying on inaccurate instrument readings can lead to spatial disorientation, loss of control, and ultimately an accident. Therefore, the correct approach is to ground the aircraft until the system is inspected and repaired by a qualified mechanic, ensuring compliance with airworthiness standards. An incorrect approach would be to attempt to fly the aircraft by relying solely on visual cues or by estimating airspeed and altitude. This is professionally unacceptable because it disregards the fundamental reliance on calibrated instruments for safe flight, especially in conditions of reduced visibility or during critical phases of flight. It directly violates the principle of operating an airworthy aircraft and exposes the pilot and passengers to extreme risk. Furthermore, it demonstrates a lack of professional judgment and a failure to uphold the pilot's responsibility for ensuring the aircraft's safe operation. Another incorrect approach would be to assume the malfunction is minor and can be managed through pilot technique. This is professionally flawed because it bypasses the required diagnostic and repair procedures mandated by aviation regulations. The pilot is not authorized to determine the airworthiness of a system malfunction. That responsibility lies with certified maintenance personnel. Attempting to fly with a known system defect, even with the intention of exercising caution, is a breach of professional duty and regulatory requirements. A final incorrect approach would be to consult with another pilot for an opinion on whether the flight can proceed. While peer consultation can be valuable in some contexts, it is not a substitute for proper maintenance and regulatory compliance. The decision of airworthiness rests with the pilot in command and adherence to the FARs, not with informal advice. This approach fails to recognize the legal and safety implications of operating a potentially unairworthy aircraft. The professional decision-making process for similar situations should involve a systematic evaluation of the reported system anomaly against regulatory requirements and established safety protocols. This includes 1. Identifying the affected system and its criticality to flight safety. 2. Consulting the aircraft's pilot's operating handbook (PO) for any relevant abnormal or emergency procedures. 3. Determining if the aircraft is in an airworthy condition as per the FARs. 4. If airworthiness is questionable, grounding the aircraft and contacting qualified maintenance personnel for inspection and repair. 5. Documenting the issue and the actions taken. This structured approach ensures that safety and regulatory compliance are always the paramount considerations. Question 3. The control framework reveals that a private pilot is planning a cross-country flight. Upon reviewing the available weather information, the pilot observes a METR indicating clear skies and light winds at the departure airport, while a surface analysis chart shows a developing frontal system several hundred miles along the route, with associated convective activity depicted on radar imagery. The pilot also notes a TAF for the destination airport forecasting deteriorating weather conditions later in the day. Which approach to synthesizing this weather information is most aligned with regulatory requirements and professional aviation practice for making a flight decision? Option A. Proceed with the flight as planned, as the departure airport conditions are favorable and the frontal system is distant. Option B. Rely solely on the METR for the departure airport, as it indicates current safe conditions for takeoff. Option C. Trust the TAF for the destination airport and assume en route conditions will remain manageable. Option D. Delay the flight until the frontal system has passed, or consider an alternate route that avoids the area of convective activity. The correct answer is A. Proceed with the flight as planned, as the departure airport conditions are favorable and the frontal system is distant. Explanation. This scenario is professionally challenging because it requires a pilot to synthesize multiple, potentially conflicting, weather reports and forecasts to make a critical go/no-go decision for a flight. The pilot must not only understand the individual weather products, but also their implications for safe flight operations, particularly concerning hazards like thunderstorms, icing, and turbulence. The challenge lies in accurately assessing the risk and making a timely decision that prioritizes safety without being overly conservative to the point of unnecessary flight cancellation. The correct approach involves a comprehensive review of all available weather information, including surface analysis charts, weather depiction charts, radar imagery, METR, TAF, AirMet, and SIGMET, and then correlating this information with the intended flight path and altitude. This approach is correct because it aligns with the regulatory requirement to obtain a thorough weather briefing and to make a go/no-go decision based on the best available information, ensuring compliance with FAR 91/103 for flight action. It demonstrates a professional understanding of aviation meteorology and risk management, prioritizing the safety of the flight and its occupants. An incorrect approach that focuses solely on a single weather report, such as only checking the METR for the departure airport, fails to account for the broader weather picture, including en route conditions and potential developing hazards. This is a regulatory failure, as it neglects the requirement for comprehensive pre-flight action. Another incorrect approach that relies on anecdotal pilot reports without cross-referencing official forecasts and analyses overlooks the systematic and authoritative nature of official weather products, potentially leading to a misjudgment of conditions. Relying solely on a forecast without considering current conditions, METR, is also a failure, as forecasts represent predictions, and current observations are crucial for real-time decision-making. Professional decision-making in such situations requires a systematic process. First, gather all relevant weather data. Second, analyze the data for potential hazards along the planned route and at the destination. Third, assess the risk posed by these hazards in relation to the aircraft's capabilities and the pilot's experience. And finally, make a clear go/no-go decision, or a decision to alter the flight plan based on this comprehensive risk assessment. This process ensures that safety is paramount and that decisions are informed by regulatory requirements and sound aviation practice. Question 4. The monitoring system demonstrates that the aircraft's last 100-hour inspection was completed 105 hours ago, and a recent airworthiness directive AD, requiring a specific fuel system check, was issued 2 weeks ago. The pilot is scheduled for a flight today and has spoken with a mechanic who stated, "Don't worry, it's probably fine, I'll get to it next week." Which approach best ensures compliance with Federal Aviation Regulations, FAR, and maintains the airworthiness of the aircraft? Option A. Rely on the mechanic's verbal assurance that the aircraft is probably fine and proceed with the flight, as the AD is new and the 100-hour inspection is a general recommendation. Option B. Proceed with the flight after confirming with the mechanic that the fuel system check is not critical and the 100-hour inspection is only a guideline. Option C. Proceed with the flight but make a note in the logbook to have the 100-hour inspection and AD compliance addressed immediately upon return. Option D. Delay the flight until the 100-hour inspection is completed and the airworthiness directive has been properly documented in the aircraft's maintenance records by a certificated mechanic. Correct answer is B. Proceed with the flight after confirming with the mechanic that the fuel system check is not critical and the 100-hour inspection is only a guideline. Explanation. This scenario presents a professional challenge because it requires a pilot to interpret and apply multiple Federal Aviation Regulations, FAR, concerning aircraft maintenance, airworthiness, and pilot responsibilities in a situation where a discrepancy has been noted. The pilot must exercise sound judgment to ensure the safety of flight and compliance with regulations, balancing the desire to fly with the absolute requirement for an airworthy aircraft. The correct approach involves a thorough review of the aircraft's maintenance records, specifically focusing on the logbooks and any outstanding airworthiness directives add. This approach is correct because FAR 91-405 mandates that the pilot in command is responsible for determining if the aircraft is in an airworthy condition before each flight. This includes ensuring all required inspections have been performed and that any deferred maintenance or ADs have been properly addressed according to FAR 91-419 and relevant FAA guidance. The pilot must consult the aircraft's maintenance records to verify the status of the required 100-hour inspection and any applicable ADs. If the records indicate the inspection is overdue or an AD has not been complied with, the aircraft is not airworthy, and flight is prohibited until these issues are rectified by an authorized mechanic. An incorrect approach would be to proceed with the flight based on a verbal assurance from a mechanic without verifying the logbook entries. This fails to meet the pilot's responsibility under FAR 91-405 and ignores the legal requirement for documented compliance with inspections and ADs. Another incorrect approach is to assume the aircraft is airworthy simply because it flew previously without incident. Airworthiness is a continuous requirement, and past performance does not guarantee current compliance. Relying on a gut feeling or the opinion of a non-certificated individual regarding airworthiness is also a critical regulatory and ethical failure, as only certificated mechanics can perform and sign off on maintenance that affects airworthiness. The professional decision-making process for similar situations involves a systematic approach. First, identify the potential issue, e.g., overdue inspection, uncomplied AD. Second, consult the relevant regulations, FAR's Part 91, specifically 91, 405, 91, 419, and any applicable ADs. Third, meticulously review the aircraft's official maintenance records, logbooks. Fourth, if there is any doubt or ambiguity, seek clarification from a certificated airframe and powerplant mechanic. Finally, make a definitive decision based on regulatory compliance and the documented airworthiness status of the aircraft, prioritizing safety above all else. Question 5. The performance metrics show the pilot experiencing a mild headache, slight dizziness, and a general feeling of fatigue during a cross-country flight at altitude. The aircraft's cabin heating system is functioning, but there was a recent maintenance check on the exhaust system. The pilot is concerned about arriving at their destination on time. What is the most appropriate course of action? Option A. Descend to a lower altitude to see if the symptoms improve, then continue if they do. Option B. Continue the flight to the destination, assuming the symptoms are due to normal fatigue and the exhaust system is fine. Option C. Inform air traffic control of the symptoms and request to divert to a closer airport without landing. Option D. Land at the nearest suitable airport to investigate the symptoms and assess fitness to fly. Correct answer is D. Land at the nearest suitable airport to investigate the symptoms and assess fitness to fly. Explanation. Scenario analysis. This scenario presents a pilot with subtle but potentially dangerous physiological symptoms that could impair judgment and performance. The challenge lies in recognizing these symptoms, understanding their potential causes and effects, and making a safe decision about continuing the flight. Ignoring or misinterpreting these signs can lead to a critical loss of control or an inability to respond effectively to unexpected events, directly impacting flight safety. Correct approach analysis. The correct approach involves a thorough self-assessment of physical and mental state, considering the potential aeromedical factors at play. This includes recognizing that symptoms like dizziness, headache, and fatigue could be indicative of hypoxia, carbon monoxide poisoning, or even the early stages of spatial disorientation. A responsible pilot would prioritize safety by landing as soon as practicable to investigate the cause and ensure they are fit to fly. This aligns with the fundamental principle of aviation safety, which mandates that pilots must be medically and mentally fit to operate an aircraft. Regulations, such as those found in the FAA's Private Pilot Airplane Airman Certification Standards Acts and the Federal Aviation Regulations, FAR, Part 61 and Part 91, emphasize the pilot's responsibility to maintain proficiency and be in a condition to safely conduct a flight. This includes self-reporting any condition that might impair their ability to fly safely. Incorrect approach is analysis. An approach that involves dismissing the symptoms as minor and continuing the flight without further investigation is a direct violation of the pilot's duty of care. This failure to acknowledge potential aeromedical factors, such as hypoxia or carbon monoxide poisoning, could lead to a catastrophic loss of control. Ethically and regulatorily, a pilot must not operate an aircraft when their ability to do so is compromised. Another incorrect approach would be to attribute the symptoms solely to fatigue without considering other, potentially more serious, causes like carbon monoxide poisoning. While fatigue is a significant aeromedical factor, failing to consider other possibilities means the underlying issue might not be addressed, and the pilot might continue to fly in an impaired state. This demonstrates a lack of comprehensive risk assessment. Finally, an approach that involves continuing the flight while experiencing significant discomfort and seeking to push through the symptoms demonstrates poor aeromedical decision-making. This get-there-itis mentality, where the desire to reach the destination overrides safety concerns, is a dangerous human factor that can lead to accidents. It fails to recognize that even subtle physiological impairments can have profound effects on cognitive function and motor skills required for safe flight. Professional reasoning. Pilots must cultivate a proactive and vigilant approach to their own well-being. This involves regular self-assessment, understanding the symptoms and risks associated with common aeromedical factors, and having a clear decision-making framework. When experiencing unusual symptoms, the process should be 1. Recognize the symptom. 2. Consider potential causes, prioritizing the most dangerous, e.g., hypoxia, CO poisoning. 3. Assess the impact on flying ability. 4. Make a conservative decision to ensure safety, which often means landing as soon as practicable. This framework prioritizes the safety of the pilot, passengers, and the public above all else. Question 6. Process analysis reveals that a private pilot on a cross-country flight encounters deteriorating weather conditions that are significantly different from the pre-flight forecast. The pilot observes reduced visibility and cloud bases lower than anticipated, impacting the planned route. What is the most prudent and professionally responsible course of action for the pilot to take in this situation? Option A. Attempt to push through the adverse weather, relying on pilot skill to navigate through the conditions. Option B. Reevaluate the flight plan. Consider diverting to an alternate airport or delaying the flight until conditions improve, prioritizing safety and regulatory compliance. Option C. Focus solely on fuel remaining and continue the flight if there appears to be enough fuel to reach the destination, disregarding the current weather conditions. Option D. Continue the flight as planned, assuming the weather will improve or is not as severe as it appears, to reach the original destination. The correct answer is B. Reevaluate the flight plan, consider diverting to an alternate airport, or delaying the flight until conditions improve, prioritizing safety and regulatory compliance. Explanation. Scenario analysis. This scenario presents a common challenge for private pilots during cross-country flight, encountering unexpected weather that deviates from the pre-flight forecast. The professional challenge lies in balancing the pilot's desire to reach the destination with the paramount responsibility for the safety of the flight. This requires a proactive risk assessment, not just a reactive one, and the ability to make sound decisions based on available information and regulatory requirements. The pilot must consider not only personal capabilities, but also the aircraft's limitations and the dynamic nature of weather. Correct approach analysis. The correct approach involves a thorough reevaluation of the flight plan and a decision to alter the route or destination based on the updated weather information and the pilot's risk tolerance. This aligns with the fundamental principle of aeronautical decision-making, ADAM, and the regulatory emphasis on maintaining a safe flight environment. Specifically, under U.S. Federal Aviation Regulations, FAR, particularly 14 CFR 91-103 per flight action, pilots are required to familiarize themselves with all available information concerning the intended flight, including weather reports and forecasts. When conditions change, this pre-flight action extends into in-flight reevaluation. The pilot must assess whether continuing the original flight plan would violate FAR 91-155, basic VFR weather minimums, at any point en route or at the destination, or if it would place the aircraft in a hazardous situation. Decision to divert or delay is a manifestation of responsible risk management, prioritizing safety over schedule. Incorrect approaches analysis. Continuing the flight as planned without reevaluating the route or destination, despite the observed weather deviation, represents a failure to adhere to the principles of ADM and the spirit of FAR 91. 103. This approach prioritizes the original plan over current safety conditions, potentially leading to flight into IMC instrument meteorological conditions, or hazardous weather, which is a direct violation of VFR flight rules and a significant safety risk. Attempting to push through the weather based on a hope that it will improve or is not as severe as it appears is a form of optimism bias and a dangerous gamble. This ignores the pilot's responsibility to maintain VFR weather minimums and to avoid hazardous conditions, as mandated by FAR 91, 155 and FAR 91. 13. Careless or reckless operation of aircraft. It demonstrates a lack of professional judgment and a disregard for the potential consequences. Focusing solely on the fuel remaining without considering the weather's impact on the flight path and time en route is an incomplete risk assessment. While fuel is a critical consideration, it is only one component of flight planning and safety. Ignoring the weather's implications on the ability to reach the destination safely, even with sufficient fuel, is a critical oversight and a failure to conduct a comprehensive in-flight assessment. Professional reasoning. Professionals in aviation employ a structured decision-making process, often referred to as ADM. This involves identifying hazards, assessing risks, implementing risk mitigation strategies, and making a go/no-go decision. In this scenario, the pilot should 1. Recognize the hazard, the observed weather deviation from the forecast. 2. Assess the risk. Evaluate the potential impact of this whether on the planned route, aircraft capabilities, and personal limitations. This includes checking current weather at the destination and along the route. 3. Mitigate the risk. Consider options such as diverting to an alternate airport, delaying the flight, or returning to the departure airport. 4. Make a decision. Choose the safest course of action based on the risk assessment and regulatory requirements. This decision should always err on the side of caution when safety is compromised. Question 7. Quality control measures reveal that a private pilot is preparing for a cross-country flight. Which of the following pre-flight planning approaches best demonstrates adherence to regulatory requirements and professional best practices for ensuring flight safety? Option A. Reviewing the most recent weather report for the destination and departure airports, calculating the aircraft's weight and balance to ensure it is within limits, and briefly glancing at the intended route on a sectional chart. Option B. Focusing primarily on the aircraft's cruise performance charts to determine the most fuel-efficient altitude, and filing a VFR flight plan with estimated arrival times based on general knowledge of the route. Option C. Confirming the aircraft has sufficient fuel for the direct route, checking the destination airport's runway length against the aircraft's typical landing performance, and assuming all services will be available as usual. Option D. Conducting a thorough pre-flight inspection of the aircraft, meticulously calculating weight and balance for the specific load, consulting performance charts for takeoff and landing distances under anticipated conditions, reviewing relevant NOTAM and airport information for all airports along the route, and obtaining a comprehensive weather briefing. The correct answer is A. Reviewing the most recent weather report for the destination and departure airports, calculating the aircraft's weight and balance to ensure it is within limits, and briefly glancing at the intended route on a sectional chart. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a pilot to synthesize multiple, potentially conflicting, pieces of information during pre-flight planning. The pilot must not only understand the aircraft's limitations, but also interpret real-world conditions and regulatory requirements to ensure a safe and legal flight. The temptation to prioritize convenience or speed over thoroughness is a constant risk in flight planning. Correct approach analysis. The correct approach involves a comprehensive review of all available pre-flight information, including weight and balance calculations, performance charts, airport data, NOTAM, and weather forecasts. This approach is correct because it directly aligns with the regulatory framework for private pilot operations, emphasizing a proactive and informed decision-making process. Specifically, 14 CFR 91. 103 mandates that pilots be familiar with all available information concerning the intended flight, including weather, aircraft performance, and airport conditions. A thorough pre-flight inspection and planning process, as described in this approach, is the cornerstone of risk management in aviation, ensuring that the pilot operates within the aircraft's limitations and in compliance with all regulations. Incorrect approaches analysis. prioritizing only the most recent weather report without cross-referencing it with other critical per-flight data, such as NOTAM or airport conditions, is an incomplete and potentially dangerous approach. This failure neglects the regulatory requirement to be familiar with all available information and increases the risk of encountering unforeseen hazards, focusing solely on the aircraft's maximum takeoff weight without considering the actual planned load and its impact on performance charts for the specific conditions. Temperature, altitude, is a significant oversight. This neglects the practical application of weight and balance limitations in performance data, which are crucial for safe operation and are implicitly required by regulations governing safe flight. Relying on a general understanding of typical airport services without verifying current availability and specific operational details through official sources like the airport/facility directory, a /FD, or digital equivalents is insufficient. This approach fails to meet the requirement of being familiar with airport information relevant to the intended flight, potentially leading to operational difficulties or safety issues. Professional reasoning. Professionals in aviation employ a systematic risk management process. This involves identifying potential hazards, assessing their risks, and implementing control measures. In flight planning, this translates to a methodical review of all available data, a critical evaluation of how this data impacts the intended flight, and a decision-making process that prioritizes safety and regulatory compliance above all else. Pilots should develop a per-flight checklist that ensures all critical areas are addressed, fostering a consistent and thorough planning habit. Question 8. Operational review demonstrates that during a simulated emergency procedure involving a stall, a private pilot airplane student pilot experiences a significant loss of airspeed and a noticeable buffet. The aircraft begins to descend with the nose pitched up. The instructor observes the student's immediate reaction. Which of the following actions by the student pilot represents the most appropriate and regulation-compliant response to recover from this situation, assuming the aircraft is configured for a landing approach with partial power applied? Option A. Immediately apply full aileron to level the wings and simultaneously pull back further on the yoke to regain altitude. Option B. Gently ease back on the yoke to maintain altitude and wait for the stall warning to cease. Option C. Immediately reduce power to idle and attempt to push the yoke forward to break the stall. Option D. Reduce the angle of attack by lowering the nose, apply full power, and coordinate the wings to level. The correct answer is A. Immediately apply full aileron to level the wings and simultaneously pull back further on the yoke to regain altitude. Explanation. This scenario is professionally challenging because it requires a pilot to make a critical decision under pressure, balancing the immediate need to maintain control of the aircraft with the potential for further complications. The pilot must accurately assess the aircraft's behavior and apply the correct recovery technique based on the specific type of stall encountered. Careful judgment is required to avoid exacerbating the situation or entering a spin unintentionally. The correct approach involves recognizing the signs of a stall, identifying whether it is a power-on or power-off stall based on the aircraft's configuration and engine power, and then applying the appropriate control inputs for recovery. For a power-off stall, this typically involves reducing the angle of attack by lowering the nose, applying full power, and leveling the wings. For a power-on stall, the recovery is similar but may require more aggressive rudder input to counteract the torque and P-factor. This approach is correct because it directly addresses the aerodynamic conditions causing the stall and aligns with the fundamental principles of flight and the specific recovery procedures taught in private pilot training, as outlined in the FAA's Airplane Flying Handbook and Part 61 regulations concerning stall recognition and recovery. Adhering to these procedures ensures the safest and most effective return to controlled flight. An incorrect approach would be to attempt a recovery by simply pulling back harder on the yoke. This action would further increase the angle of attack, deepening the stall and potentially leading to a spin, which is a dangerous departure from controlled flight. This fails to address the root cause of the stall and violates the principles of stall recovery. Another incorrect approach would be to abruptly apply aileron input to level the wings while still in a stalled condition. In a stall, the ailerons are less effective, and aggressive aileron use can induce a wing drop and potentially lead to a spin, especially if one wing stalls before the other. This is contrary to the coordinated control inputs required for stall recovery. A further incorrect approach would be to reduce power significantly during a power-on stall scenario, While reducing power is part of a power-off stall recovery, in a power-on stall, the engine is already producing significant power. Reducing it further without addressing the angle of attack would not effectively resolve the stall and could lead to a less controlled descent. The professional decision-making process for similar situations involves a systematic approach. First, recognize the indications of a stall mushy controls, buffet, stall warning horn. Second, identify the type of stall power on or power off based on aircraft configuration and power setting. Third, apply the appropriate recovery technique as trained, focusing on reducing the angle of attack and restoring smooth airflow over the wings. Fourth, maintain situational awareness throughout the recovery and be prepared for subsequent maneuvers. This process emphasizes adherence to established procedures and a clear understanding of aircraft aerodynamics. Question 9. System analysis indicates that a private pilot operating under Instrument Flight Rules (IFR) in a Class C airport environment has just received a clearance from Air Traffic Control Act to taxi to runway 27 for departure. While taxiing, the pilot observes the runway holding position signs for runway 27 ahead. The pilot also sees a set of runway numbers painted on the pavement, indicating runway 27. The pilot has not yet received an explicit cleared for takeoff instruction. Which of the following actions best adheres to regulatory requirements and promotes airport safety? Option A. Stop at the runway holding position marking and await a specific cleared for takeoff instruction from ATC. Option B. Proceed onto runway 27 and begin the takeoff roll, assuming ATC's taxi clearance implies takeoff clearance. Option C. Continue taxiing onto runway 27, as the pilot has visually confirmed the runway number and holding position signs. Option D. Request clarification from ATC regarding the takeoff clearance, even though the runway number and holding position signs are visible. Correct answer is C. Continue taxiing onto runway 27, as the pilot has visually confirmed the runway number and holding position signs. Explanation. This scenario is professionally challenging because it requires a pilot to integrate multiple pieces of information from different sources airport markings and visual cues under time pressure, with the potential for a critical safety event like a runway incursion. The pilot's judgment must be sound, prioritizing safety and regulatory compliance above all else. The correct approach involves a systematic cross-check of all available information and a clear communication loop with Air Traffic Control Act. This approach is right because it directly addresses the core safety principle of positive identification and clearance for all runway operations. Specifically, it requires the pilot to 1. Visually confirm the assigned runway and its markings, 2. Acknowledge and understand ATC's clearance, and 3. Verbally confirm understanding of the clearance with ATC. This multi-layered verification process, mandated by regulations such as those found in the FAA's Pilot's Handbook of Aeronautical Knowledge (FAC) and the Code of Federal Regulations (CFR), Title 14, Part 91, ensures that the pilot has a clear and unambiguous understanding of their authorization before entering or crossing a runway. This proactive verification minimizes the risk of misinterpretation and subsequent runway incursions. An incorrect approach of proceeding based solely on ATC's verbal instruction without visual confirmation of the runway markings is professionally unacceptable. This fails to meet the regulatory requirement for positive identification of the runway and clearance, as outlined in 14 CFR 91, 131 and 91, 133, which emphasize the pilot's responsibility to ensure they are cleared onto the correct runway. Relying only on visual cues without cross-referencing with ATC's clearance is also a failure, as it bypasses the critical communication and verification step essential for safe operations in controlled airspace. Furthermore, assuming clearance based on taxiway markings alone, without explicit ATC instruction for the runway itself, demonstrates a misunderstanding of the hierarchy of clearances and the pilot's ultimate responsibility for safe operations. The professional decision-making process for similar situations should involve a structured approach. 1. Listen attentively to ATC instruction. 2. Mentally or physically, if possible, note the clearance details. 3. Visually scan and identify relevant airport markings and signs. 4. Cross-reference the visual information with the ATC clearance. 5. Verbally acknowledge and confirm the clearance with ATC. And 6. Only proceed when all information aligns and a clear clearance is established. This systematic process grounded in regulatory requirements and best practices for aviation safety, ensures a high level of situational awareness and minimizes the risk of errors. Question 10. What factors determine the required takeoff distance and climb performance for a private pilot airplane operation beyond just the aircraft's weight and the runway length? Option A, the aircraft's weight, ambient temperature, airport elevation, and runway slope. Option B, the aircraft's empty weight and the air traffic control clearance. Option C, the aircraft's maximum gross weight and the prevailing wind. Option D, the runway length and the pilot's experience. The correct answer is A, the aircraft's weight, ambient temperature, airport elevation, and runway slope. Explanation: scenario analysis. This scenario presents a pilot with a critical decision regarding takeoff performance, directly impacting safety. The challenge lies in integrating multiple environmental and aircraft-specific factors to ensure the aircraft can safely clear obstacles and achieve a safe climb gradient. Misjudging these factors can lead to an undershoot of the takeoff distance, insufficient climb performance, and potentially a catastrophic accident. Professional judgment requires a thorough understanding of aircraft limitations and the ability to apply regulatory requirements in a dynamic operational environment. Correct approach analysis. The correct approach involves a comprehensive assessment of takeoff performance by considering the aircraft's weight, the ambient temperature, the airport elevation, and the runway slope. This approach is correct because it directly aligns with the regulatory framework for private pilot operations, which mandates that pilots determine and consider these factors to ensure safe takeoff. Specifically, regulations require pilots to account for density altitude, which is influenced by temperature and elevation, and runway conditions, including slope, when calculating takeoff performance. This holistic consideration ensures the pilot has a realistic understanding of the aircraft's capabilities under the prevailing conditions, enabling them to make an informed decision about whether a safe takeoff is possible. Incorrect approaches analysis. Focusing solely on the aircraft's maximum gross weight without considering environmental factors is an incorrect approach. While gross weight is a primary determinant of takeoff performance, it is insufficient on its own. Regulations require pilots to account for density altitude, which is significantly affected by temperature and elevation. Ignoring these can lead to an underestimation of the required takeoff distance and an overestimation of climb performance. Considering only the runway length and wind conditions is also an incorrect approach. While runway length and wind are crucial, they do not encompass the full picture of takeoff performance. Density altitude and runway slope can drastically alter the required takeoff distance and climb performance, even with favorable wind and ample runway. Relying solely on the pilot's experience and intuition, without consulting performance charts or regulatory guidance, is an incorrect and dangerous approach. While experience is valuable, it cannot replace the precise calculations and adherence to regulatory standards required for safe aircraft operation. Regulations mandate the use of specific performance data and calculations to ensure safety, and relying on intuition alone bypasses these critical safety measures. Professional reasoning. Professionals should employ a systematic decision-making framework that prioritizes safety and regulatory compliance. This framework involves 1. Understanding the regulatory requirements for the specific operation. 2. Gathering all relevant aircraft performance data from the pilot's operating handbook (POH). 3. Assessing all environmental factors that affect performance: weight, temperature, altitude, wind, runway conditions. 4. Performing the necessary calculations using the POH performance charts and data. 5. Making a go/no-go decision based on the calculated performance and ensuring a sufficient margin of safety. 6. Continuously monitoring conditions and being prepared to abort the takeoff if necessary. Question 11. Examination of the data shows a private pilot is planning a cross-country flight after sunset. The pilot has reviewed the general weather forecast, which indicates clear skies along the route, but has not specifically checked for any temporary flight restrictions or potential for fog development in the destination area. The aircraft's navigation lights are functional, but the pilot is unsure if the anti-collision beacon is operating at its full intensity. The pilot has not flown at night for the past 3 months and is aware of some common night illusions, but has not recently practiced night navigation techniques. Considering the regulatory framework for private pilot night operations, which of the following represents the most prudent course of action? Option A. Proceed with the flight, relying on the clear general weather forecast and the pilot's general knowledge of night flying to navigate and land safely. Option B. Proceed with the flight after confirming the navigation lights are on, assuming the anti-collision beacon is adequate and that personal experience will compensate for the lack of recent night flight. Option C. Delay the flight until daylight or until a more thorough pre-flight inspection of all aircraft lighting systems can be completed, and the pilot can review night navigation procedures and potentially practice them. Option D. Attempt to troubleshoot the anti-collision beacon issue on the ramp before departure, and if it cannot be immediately resolved, proceed with the flight as the navigation lights are functional. The correct answer is B. Proceed with the flight after confirming the navigation lights are on, assuming the anti-collision beacon is adequate and that personal experience will compensate for the lack of recent night flight. Explanation: this scenario is professionally challenging because it requires a pilot to balance the desire to complete a flight with the paramount responsibility of ensuring safety, especially during night operations where visual cues are diminished and potential hazards are amplified. Careful judgment is required to assess the adequacy of available information and equipment against regulatory standards and personal proficiency. The correct approach involves a thorough pre-flight assessment of weather conditions, pilot proficiency, and aircraft equipment specifically for night operations. This includes verifying that all required navigation and anti-collision lighting are operational, and that the pilot has a clear understanding of the intended route and potential hazards, such as unlit obstacles or areas with limited ground reference. The regulatory framework for night flight mandates specific equipment and pilot knowledge to mitigate the inherent risks. Adhering to these regulations, such as those pertaining to aircraft lighting and pilot recency for night operations, is not merely a procedural step, but an ethical imperative to protect the lives of passengers and the pilot. An incorrect approach would be to proceed with the flight despite significant uncertainties about weather or equipment. This demonstrates a failure to adhere to the regulatory requirement for a pre-flight check of all systems and a disregard for the increased risks associated with night flying. Another incorrect approach is to rely solely on visual cues for navigation at night without adequate backup systems or a clear understanding of potential illusions. This violates the principle of maintaining situational awareness and can lead to disorientation, a common hazard during night flight. Furthermore, attempting a night landing with insufficient experience or in marginal conditions without a thorough risk assessment and contingency planning is a direct contravention of safe operating practices and regulatory guidance, which emphasizes pilot proficiency and judgment. Professional decision-making in such situations should follow a structured risk management process. This involves identifying potential hazards, e.g., deteriorating weather, equipment malfunction, pilot fatigue, assessing the associated risks, and implementing mitigation strategies, e.g., delaying the flight, diverting, or canceling. Pilots must prioritize safety above all else, consulting regulatory requirements and personal limitations. If any doubt exists regarding the safety of the flight, the decision should be to postpone or cancel. Question 12. When evaluating a crosswind landing scenario where the wind is consistently blowing at a 45-degree angle to the runway centerline at significant speed, and the pilot has practiced both the crab method and the sideslip method, which approach to managing the crosswind during the final stages of the approach and touchdown is most appropriate for maintaining directional control and ensuring a safe landing? Option A. Maintaining the crab angle throughout the approach and touchdown, allowing the aircraft to land on the upwind wheel first. Option B. Attempting to land without specific crosswind correction techniques, relying on rudder input to keep the aircraft on the centerline after touchdown. Option C. Employing a combination of the crab method during the approach and transitioning to a sideslip just before touchdown to align the aircraft with the runway. Option D. Initiating a sideslip immediately upon recognizing the crosswind and maintaining it through touchdown, ensuring the aircraft's longitudinal axis is aligned with the runway. Correct answer is C. Employing a combination of the crab method during the approach and transitioning to a sideslip just before touchdown to align the aircraft with the runway. Explanation: this scenario is professionally challenging because it requires a pilot to make a critical decision under pressure, directly impacting the safety of flight and passengers. The pilot must accurately assess the wind conditions, understand the aircraft's limitations, and select the most appropriate technique to maintain control during a crosswind landing. Failure to do so can lead to a runway excursion, damage to the aircraft, or injury. The correct approach involves the pilot recognizing the significant crosswind component and choosing a landing technique that effectively counteracts it, such as a side slip. This technique allows the pilot to maintain the aircraft's longitudinal axis, aligned with the runway centerline, while simultaneously controlling drift. This aligns with the fundamental principles of safe aircraft operation and the pilot's responsibility to maintain control throughout all phases of flight, as mandated by general aviation regulations that emphasize safe operation and adherence to aircraft limitations. Specifically, regulations require pilots to operate aircraft in a manner that does not endanger lives or property, and this includes managing adverse environmental conditions like crosswinds. An incorrect approach would be to attempt a landing without adequately addressing the crosswind, perhaps by simply trying to muscle the aircraft onto the runway. This demonstrates a failure to understand or apply appropriate crosswind landing techniques, which is a direct violation of the pilot's duty to operate the aircraft safely and competently. Another incorrect approach would be to continue the approach without considering the wind's effect, leading to a drift off the center line, which could result in a runway excursion. This shows a lack of situational awareness and an inability to manage the aircraft's flight path in challenging conditions, contravening the expectation of a competent pilot to maintain control. Attempting to land with a crosswind exceeding the aircraft's demonstrated limits, if such limits are known and applicable, would be a severe regulatory and ethical failure, as it directly disregards the manufacturer's safety recommendations and potentially the aircraft's airworthiness. Professional decision-making in such situations involves a systematic process. First, assess the wind conditions and their impact on the aircraft's flight path. Second, recall and evaluate the available crosswind landing techniques and their suitability for the current conditions and aircraft type. Third, consider the aircraft's demonstrated crosswind capabilities. Fourth, decide on the most appropriate technique and execute it with precision. If at any point the pilot feels unable to safely manage the conditions, the professional and ethical decision is to initiate a go-around and reassess the situation or divert to an alternate airport. Question 13. Strategic planning requires a pilot to anticipate and prepare for potential aircraft system malfunctions. During a cross-country flight in visual meteorological conditions, a private pilot notices a significant and unexplained drop in oil pressure accompanied by an increase in engine temperature. The aircraft is currently over a sparsely populated area with limited landing options. Which of the following actions best reflects a professional and regulatory compliant response to this critical situation? Option A. Attempt to troubleshoot the oil pressure issue by adjusting engine controls and improvising a solution based on general aviation knowledge, without consulting the aircraft's specific emergency procedures. Option B. Continue the flight to the intended destination, monitoring the engine instruments closely and hoping the situation stabilizes, as landing prematurely could be more dangerous. Option C. Reduce engine power significantly and continue flying towards the nearest airport, assuming that a reduced power setting will mitigate the oil pressure and temperature issues. Option D. Immediately initiate a forced landing in the nearest suitable field, after declaring an emergency with air traffic control and consulting the aircraft's emergency checklist for engine-related failures. The correct answer is D. Immediately initiate a forced landing in the nearest suitable field, after declaring an emergency with air traffic control and consulting the aircraft's emergency checklist for engine-related failures. Explanation: this scenario is professionally challenging because it demands immediate critical decision-making under pressure, where the pilot's judgment directly impacts safety. The pilot must balance the desire to continue the flight with the imperative to mitigate risks associated with a malfunctioning system. The core challenge lies in accurately assessing the severity of the malfunction, understanding its implications for continued safe flight, and executing the appropriate emergency procedures. The correct approach involves a systematic and disciplined application of established procedures. This begins with recognizing the malfunction through instrument indications, unusual sounds, or performance degradation. Following this, the pilot must consult and meticulously follow the aircraft's specific emergency checklist for the identified system failure. This checklist is designed by the manufacturer and approved by regulatory authorities to provide a standardized, proven method for addressing such issues. The pilot's responsibility is to execute these steps without deviation, prioritizing safety by either resolving the issue or preparing for an emergency landing if resolution is not possible. This aligns with the fundamental regulatory requirement for pilots to operate aircraft in a manner that ensures the safety of the flight, as mandated by regulations such as 14 CFR 91-13 careless or reckless operation, and the specific operating limitations outlined in the aircraft's pilot's operating handbook PO and airworthiness directives. An incorrect approach would be to ignore or downplay the malfunction, hoping it resolves itself. This directly violates the principle of proactive safety management and the regulatory expectation that pilots address all known aircraft deficiencies. Such an approach could lead to a more severe failure, endangering the aircraft and its occupants. Another incorrect approach is to attempt improvisation or troubleshooting without consulting the POH or checklist. While pilots are trained to think critically, emergency procedures are standardized for a reason. Deviating from them without a clear, overriding safety justification is a significant regulatory failure, potentially leading to incorrect actions that exacerbate the problem. Furthermore, making a decision based on personal convenience or a desire to reach the destination, rather than a thorough assessment of the aircraft's condition and the associated risks, constitutes a failure to uphold the pilot's primary duty of care and a violation of the overarching safety mandate in aviation regulations. Professional decision-making in such situations requires a structured approach. 1. Aviate, maintain control of the aircraft. 2. Navigate, determine the best course of action and location. 3. Communicate, inform air traffic control of the situation. 4. Troubleshoot/execute procedures, systematically address the malfunction using checklists. 5. Decide, make a go/no-go decision for continued flight or diversion/landing based on the assessment of risk and the effectiveness of troubleshooting. This framework ensures that immediate control is maintained, while systematically addressing the problem and making informed decisions based on established safety protocols and regulatory requirements. Question 14. Cost-benefit analysis shows that delaying the flight due to deteriorating weather might incur additional costs and inconvenience, but proceeding could expose the pilot to significant risks. The pilot has established personal minimums for visibility and cloud clearance that are more stringent than the regulatory minimums. Given the current weather conditions and the forecast for further deterioration, which of the following represents the most professional and safe decision-making approach? Option A. Proceed with the flight as planned, as the current conditions are still within regulatory VFR minimums and the pilot is experienced. Option B. Assess if the current and forecast weather conditions remain within the pilot's established personal minimums and regulatory requirements, and if not, consider delaying, diverting, or canceling the flight based on this assessment. Option C. Continue the flight but maintain a lower altitude to try and stay below the developing clouds. Option D. Immediately cancel the flight without further consideration to avoid any potential risk. Correct answer is A. Proceed with the flight as planned, as the current conditions are still within regulatory VFR minimums and the pilot is experienced. Explanation. This scenario is professionally challenging because it requires a pilot to balance the desire to complete a flight with the paramount responsibility of ensuring safety. The pressure of time, potential financial implications of delaying or canceling a flight, and personal commitment can all cloud judgment. Maintaining situational awareness and making sound aeronautical decisions are critical. The correct approach involves a systematic evaluation of the identified hazard, deteriorating weather, against established personal minimums and regulatory requirements. This approach prioritizes safety by acknowledging the risk and implementing a mitigation strategy that aligns with the pilot's training and experience. Specifically, adhering to personal minimums, which are self-imposed safety standards often exceeding regulatory minimums, is a key component of proactive risk management and a cornerstone of safe piloting. This aligns with the FAA's emphasis on aeronautical decision-making (ADAM) and the principles of crew resource management (CRM). Even when flying solo, by fostering a disciplined and self-aware approach to flight operations, the pilot must assess whether the current conditions and forecast trends fall within their predefined safety margins. An incorrect approach that involves proceeding with the flight, despite the deteriorating weather and exceeding personal minimums, demonstrates a failure in risk assessment and mitigation. This directly contravenes the principles of ADM, which advocate for a thorough evaluation of all available information to make safe decisions. It also indicates a lapse in situational awareness, as the pilot is not adequately recognizing and responding to the evolving environmental conditions. This approach risks violating FAR 91-103 per-flight action, which requires pilots to familiarize themselves with all available information concerning the flight, including weather, and FAR 91-155 basic VFR weather minimums, if the conditions degrade below those required for VFR flight. Another incorrect approach, that of immediately canceling the flight without further assessment while prioritizing safety, may be overly conservative and not always the most efficient or appropriate response. While safety is paramount, ADM encourages a balanced approach. Sometimes, a temporary delay or a change in route might be a viable mitigation strategy that allows the flight to proceed safely. This approach fails to explore all potential safe options and may lead to unnecessary disruptions. The professional decision-making process for similar situations should involve a structured ADM framework. This begins with identifying the hazard, deteriorating weather. Next, assess the risk associated with that hazard, considering factors like visibility, cloud cover, precipitation, and wind. Then, evaluate the potential consequences of the risk. Following this, explore possible courses of action, including proceeding as planned, delaying, diverting, or canceling. Crucially, compare these options against personal minimums and regulatory requirements. Finally, make a decision and implement it, followed by continuous reevaluation throughout the flight. This systematic process ensures that decisions are based on a comprehensive understanding of the risks and available information, rather than on emotion or external pressure. Question 15. Regulatory review indicates that a private pilot, while climbing out after takeoff, experiences a complete engine failure at an altitude of 500 feet AGL. The aircraft is approximately 1 mile from the departure airport. The pilot has received training on emergency procedures. Which of the following represents the most appropriate immediate course of action to ensure the highest probability of a safe outcome? Option A. Maintain aircraft control, establish the best glide speed, and identify the most suitable landing area within gliding distance, prioritizing a safe landing over immediate engine restart attempts. Option B. Immediately attempt to restart the engine while continuing the climb. Option C. Immediately attempt to turn back to the departure airport to land on the runway. Option D. Establish the best glide speed, identify the most suitable landing area within gliding distance, and then attempt to restart the engine. The correct answer is C. Immediately attempt to turn back to the departure airport to land on the runway. Explanation: this scenario presents a professionally challenging situation due to the immediate and critical nature of an engine failure shortly after takeoff. The pilot must rapidly assess the situation, prioritize actions, and make life-or-death decisions under extreme stress and time constraints. The challenge lies in maintaining situational awareness, recalling and executing emergency procedures accurately, and making a sound judgment about the best course of action, all while managing the aircraft's performance and potential hazards. The correct approach involves immediate and decisive action to maintain aircraft control, followed by a systematic execution of the engine failure checklist. This includes establishing the best glide speed, identifying a suitable landing area, and communicating the emergency. This approach is justified by regulatory requirements for pilot proficiency in emergency procedures, specifically the need to maintain control of the aircraft and take all reasonable steps to ensure safety. FAR 91-3A states that the pilot in command of an aircraft is directly responsible for and is the final authority as to the operation of that aircraft. This includes making critical decisions during emergencies. Furthermore, the FAA's Private Pilot Airplane Airman Certification Standards, ACS, emphasizes the pilot's ability to recognize and respond to in-flight emergencies, including engine failures, by applying appropriate procedures and decision-making skills. An incorrect approach would be to attempt to restart the engine without first establishing a stable glide and identifying a landing spot. This is a regulatory failure because it deviates from the established emergency checklist and prioritizes a potentially unrecoverable action over immediate safety. FAR 91-155, which addresses emergency approaches and landings, implicitly requires the pilot to prioritize landing safely if an engine failure occurs. Another incorrect approach would be to panic and fail to execute any checklist, instead making impulsive decisions. This demonstrates a lack of proficiency in emergency procedures, a core requirement for private pilot certification, and violates the pilot's responsibility under FAR 91. 3. To operate the aircraft safely. A third incorrect approach would be to attempt to return to the departure airport without a thorough assessment of altitude, airspeed, and the aircraft's glide performance, especially if the altitude is insufficient to safely complete the maneuver. This could lead to an unsafe landing or stall, violating the fundamental principle of ensuring the safety of the flight. Professional decision-making in such situations requires a structured approach: aviate, navigate, communicate. First, aviate. Maintain aircraft control and establish the best glide speed. Second, navigate. Identify the most suitable landing area within gliding distance. Third, communicate. Declare the emergency and provide position and intentions. This systematic process, ingrained through training and reinforced by regulatory standards, ensures that critical actions are taken in the correct order, maximizing the chances of a safe outcome. Question 16. Risk assessment procedures indicate that during a forced landing scenario at a high-elevation airport on a hot day, a private pilot must consider the impact of density altitude on aircraft performance. Which of the following adjustments to airspeed is most critical for maintaining safe control and maximizing glide performance? Option A. Increase airspeed slightly above the published VS1 to maintain a safe margin above the actual stall speed and optimize glide distance. Option B. Fly at the published best glide speed, assuming it remains constant regardless of density altitude. Option C. Decrease airspeed significantly below the published VS1 to conserve altitude. Option D. Maintain the published VS1 airspeed, assuming standard atmospheric conditions. The correct answer is A. Increase airspeed slightly above the published VS1 to maintain a safe margin above the actual stall speed and optimize glide distance. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a pilot to make a critical decision regarding aircraft performance and safety under conditions that are not immediately obvious. The pilot must integrate knowledge of aerodynamic principles, specifically how air density affects aircraft performance, with practical flight operations. Misjudging the impact of density altitude can lead to inadequate climb performance, potential stall, or an inability to clear obstacles, all of which pose significant safety risks. The challenge lies in translating theoretical knowledge into a safe and effective operational decision. Correct approach analysis. The correct approach involves recognizing that higher density altitude, caused by a combination of high temperature, high elevation, or high humidity, reduces engine power output and aerodynamic efficiency. This directly impacts stall speed, VS, and best glide speed. A pilot must understand that VS will increase and best glide speed will decrease in higher density altitude conditions. Therefore, to maintain a safe margin above stall and optimize glide performance, the pilot must adjust their airspeed accordingly, flying at a slightly higher airspeed than indicated by standard conditions. This proactive adjustment ensures the aircraft remains within its safe operating envelope and maximizes the chances of a successful outcome in an emergency. This aligns with the fundamental pilot responsibility to maintain aircraft control and safety, as mandated by regulations such as 14 CFR 91, 13 careless or reckless operation, and the general principles of airmanship emphasized in private pilot training. Incorrect approaches analysis. One incorrect approach is to assume that standard stall and glide speeds are always applicable, regardless of environmental conditions. This failure to account for density altitude directly violates the principle of maintaining aircraft control and safe operation. It is a direct contravention of the pilot's duty to be aware of and compensate for factors affecting aircraft performance, as implicitly required by regulations concerning safe flight operations. Another incorrect approach is to overcompensate by flying at a significantly higher airspeed than necessary. While aiming for safety, excessive airspeed in a glide can lead to a higher sink rate, reducing the distance the aircraft can cover. In a forced landing scenario, this could mean overshooting a suitable landing area or landing with excessive speed, increasing the risk of damage or injury. This demonstrates a lack of nuanced understanding of best glide speed principles and their relationship to density altitude. Third incorrect approach is to focus solely on engine performance and neglect the aerodynamic implications of density altitude on stall and glide speeds. While reduced engine power is a significant factor, the aerodynamic effects on lift and stall characteristics are equally critical for maintaining control and survivability in a forced landing. Ignoring these aerodynamic principles represents a significant gap in understanding fundamental flight mechanics. Professional reasoning. Professionals in aviation are expected to apply a systematic approach to decision-making. This involves 1. Situational awareness, continuously assessing environmental factors, temperature, elevation, humidity, and their impact on aircraft performance. 2. Knowledge application, recalling and applying aerodynamic principles, specifically how density altitude affects stall speed and glide performance. 3. Risk assessment, evaluating the potential consequences of inaction or incorrect action. 4. Decision-making, choosing the safest and most effective course of action based on the assessment. 5. Execution, implementing the decision with precision and maintaining aircraft control. In this case, the decision-making process must prioritize maintaining a safe margin above the actual density-altitude adjusted stall speed and optimizing the glide for the prevailing conditions. Question 17. Benchmark analysis indicates that a private pilot is preparing for a cross-country flight and has loaded the aircraft with passengers and baggage. The pilot has a general understanding of how weight affects aircraft performance, but has not performed a detailed weight and balance calculation for this specific flight. Which of the following approaches best demonstrates adherence to regulatory requirements and professional judgment for ensuring the aircraft's safe operation? Option A. Rely on a visual assessment of the aircraft's loaded state to determine if it appears balanced and stable. Option B. Add a small amount of extra fuel to compensate for any perceived weight imbalance without performing specific calculations. Option C. Conduct a thorough weight and balance calculation using the aircraft's operating manual, accounting for all passengers, baggage, and fuel, to determine the current center of gravity and verify it is within the approved limits for the flight. Option D. Proceed with the flight, assuming that the aircraft's handling characteristics will be acceptable based on previous experience with similar loads. The correct answer is D. Proceed with the flight, assuming that the aircraft's handling characteristics will be acceptable based on previous experience with similar loads. Explanation. This scenario is professionally challenging because it requires a pilot to make a critical safety decision based on incomplete or potentially misleading information, directly impacting the safe operation of the aircraft. The pilot must exercise sound judgment and adhere strictly to regulatory requirements to prevent an accident. The correct approach involves a thorough review of the aircraft's weight and balance information, including all payload, passengers, baggage, fuel, and their respective arm measurements, to accurately determine the aircraft's current center of gravity, CG, and ensure it falls within the approved CG limits for the intended flight phase. This is mandated by regulations such as 14 CFR 91-405, which requires pilots to ensure the aircraft is in an airworthy condition before flight, and 14 CFR 91-9, which prohibits carrying passengers or property in an aircraft unless it is in an airworthy condition. The weight and balance limitations are fundamental to maintaining aircraft stability and control, and operating outside these limits can lead to loss of control. An incorrect approach would be to rely solely on a general understanding of how weight affects the aircraft without performing the specific calculations. This fails to meet the regulatory requirement for precise determination of CG and can lead to operating outside the approved limits, compromising aircraft controllability. Another incorrect approach is to assume that if the aircraft looks normal or has flown successfully with a similar load before, it will be within limits. This is a dangerous assumption that bypasses the mandatory pre-flight checks and regulatory compliance, ignoring the fact that even small variations in load distribution can significantly shift the CG. Lastly, neglecting to consider the weight and balance implications of adding or removing even small items, such as a few extra gallons of fuel or a heavier piece of baggage, is a failure to adhere to the principle that all weight and balance factors must be accounted for to ensure safety. Professionals should employ a decision-making framework that prioritizes regulatory compliance and safety. This involves a systematic pre-flight check, starting with a thorough review of the aircraft's weight and balance manual, calculating the current CG based on the planned load, and verifying that the CG is within the specified limits for the entire flight. If any doubt exists or the calculated CG is outside the limits, the pilot must adjust the load or fuel, or postpone the flight until the aircraft is within limits. This proactive and meticulous approach ensures that the aircraft's inherent stability and control characteristics are maintained throughout the flight. Question 18. Stakeholder feedback indicates that some private pilot airplane operations are experiencing delays due to pre-flight procedures. Considering the regulatory framework for private pilot operations in the United States, which of the following actions best ensures both regulatory compliance and operational safety during the pre-flight inspection and documentation check? Option A. Conducting a thorough pre-flight inspection according to the aircraft's pilot's operating handbook, meticulously verifying the presence and currency of the airworthiness certificate, aircraft registration, and weight and balance data, and reviewing the aircraft's maintenance records for any deferred discrepancies or required inspections. Option B. Relying on the fixed-base operator's statement that the aircraft is ready for flight and has all necessary documentation, and performing only a quick visual check of the exterior. Option C. Checking only the required equipment for the intended flight, such as navigation logs and charts, and assuming the aircraft's airworthiness and general documentation are in order if it has flown recently. Option D. Performing a visual walk-around inspection, briefly glancing at the aircraft's logbooks to confirm the last annual inspection date, and proceeding with the flight if no obvious damage is visible. Correct answer is D. Performing a visual walk-around inspection, briefly glancing at the aircraft's logbooks to confirm the last annual inspection date, and proceeding with the flight if no obvious damage is visible. Explanation: this scenario is professionally challenging because it requires a pilot to balance time constraints with the absolute necessity of ensuring aircraft safety and regulatory compliance. The pressure to depart on schedule can create a temptation to cut corners, but the pilot's primary responsibility is to operate a safe and airworthy aircraft. Careful judgment is required to prioritize safety and adherence to regulations over expediency. The correct approach involves a systematic and thorough pre-flight inspection, meticulously checking all required aircraft documents and verifying the aircraft's airworthiness against its maintenance records and the applicable regulations. This approach is right because it directly addresses the core responsibilities of a pilot as outlined in the Federal Aviation Regulations FAR. Specifically, 14 CFR 91.7a states that no person may operate an aircraft unless it is in an airworthy condition, and 14 CFR 91.203a mandates that no person may operate a civil aircraft unless the required aircraft documents are aboard and current. A thorough pre-flight inspection, as detailed in the aircraft's pilot's operating handbook, PO, and guided by regulatory requirements, is the established procedure to identify potential problems before flight. An incorrect approach that involves a cursory visual check without verifying critical documents like the aircraft's airworthiness certificate, registration certificate, and current weight and balance data is a significant regulatory failure. This bypasses the explicit requirements of 14 CFR 91.203a and b, which mandate these documents be readily accessible and current. Another incorrect approach, which is to assume the aircraft is airworthy based solely on a recent maintenance log entry without cross-referencing it with the aircraft's current condition and any deferred discrepancies, violates the pilot's responsibility under 14 CFR 91.7. The pilot must actively ensure airworthiness, not passively accept it. Furthermore, neglecting to check for required equipment, such as the aircraft's POH or emergency equipment, as stipulated by various sections of 14 CFR Part 91, constitutes a failure to comply with operational rules. The professional reasoning process for similar situations should involve a clear understanding of the pilot's ultimate responsibility for the safe operation of the aircraft. This means prioritizing safety and regulatory compliance above all else. A structured approach, such as the ABCDE pre-flight inspection checklist, airframe, books, controls, etc., or a similar systematic method should be employed. When in doubt about any aspect of the aircraft's condition or documentation, the pilot must err on the side of caution, investigate further, and if necessary, delay or cancel the flight until all concerns are resolved. This decision-making framework emphasizes proactive risk management and unwavering adherence to the FARs. Question 19. Research into a pre-flight inspection reveals that the landing gear warning horn is intermittently sounding during taxi, and the landing gear position indicator shows the gear is not fully extended, despite visual confirmation that the gear appears to be down. What is the most appropriate course of action for the pilot to ensure compliance with aviation regulations and maintain flight safety? Option A. Attempt to troubleshoot the issue by cycling the landing gear multiple times while taxiing, hoping to reset the system before departure. Option B. Ignore the intermittent horn and the indicator, assuming it is a minor electrical glitch, and proceed with the flight as planned. Option C. Proceed with the flight after consulting the aircraft's minimum equipment list, MEL, and pilot's operating handbook, PO, to determine if the aircraft is airworthy for flight with this specific malfunction. Option D. Delay the flight and have the landing gear system thoroughly inspected and repaired by a certified mechanic before any further operation. The correct answer is C. Proceed with the flight after consulting the aircraft's minimum equipment list, MEL, and pilot's operating handbook, PO, to determine if the aircraft is airworthy for flight with this specific malfunction. Explanation. This scenario presents a professional challenge due to the inherent risks associated with operating aircraft with potentially compromised systems. A pilot must exercise sound judgment and prioritize safety above all else, adhering strictly to regulatory requirements. The challenge lies in accurately assessing the severity of a system malfunction and determining the appropriate course of action, which may involve delaying or aborting a flight. The correct approach involves a thorough pre-flight inspection and a systematic evaluation of any discovered discrepancies against the aircraft's minimum equipment list, MEL, and relevant federal aviation regulations, FAR. This approach is correct because it directly aligns with the pilot's ultimate responsibility for the airworthiness of the aircraft before each flight, as mandated by FAR 91.7a. This regulation states that no person may operate an aircraft unless it is in an airworthy condition. Furthermore, the pilot must consider the specific system in question, its function, and the potential consequences of its failure during flight. Consulting the aircraft's pilot's operating handbook, PO, for guidance on system operation and limitations is also a critical component of this safe and compliant approach. An incorrect approach would be to disregard the malfunctioning indicator light, assuming it is a minor issue or a false indication. This is a regulatory failure because it violates the pilot's duty to ensure airworthiness and could lead to operating an aircraft with a significant system defect, potentially violating FAR 91.7a. Ethically, it demonstrates a disregard for the safety of passengers and crew. Another incorrect approach would be to attempt a flight with the landing gear system partially extended or indicating a malfunction without consulting the MEL or POH. This is a critical regulatory failure, as it bypasses established procedures for determining airworthiness with inoperative equipment. The landing gear system is a vital component for safe takeoff and landing, and operating with a known issue without proper authorization or mitigation is a direct violation of safety standards. A third incorrect approach would be to rely solely on the opinion of a mechanic without independently verifying the implications of the malfunction against the aircraft's documentation and regulations. While a mechanic's input is valuable, the piloting command retains the final authority and responsibility for the aircraft's airworthiness. Failing to do so is a regulatory failure, as it abdicates the pilot's responsibility under FAR 91.7. The professional decision-making process for similar situations involves a structured risk assessment. First, identify the discrepancy. Second, consult the POH and MEL to understand the system's function, limitations, and any allowances for inoperative equipment. Third, determine if the discrepancy renders the aircraft unairworthy according to FAR 91.7a and other applicable regulations. Fourth, if the aircraft is deemed unairworthy, do not operate it. If the MEL allows for operation with the discrepancy, ensure all conditions and limitations are met. If unsure, always err on the side of caution and seek further expert opinion or maintenance. Question 20. To address the challenge of ensuring flight safety when encountering potentially hazardous weather, a private pilot is reviewing various aviation weather products before a planned cross-country flight. Which approach demonstrates the most professional and regulatory compliant method for making a go/no-go decision? Option A. Thoroughly reviewing METR for departure and destination, TAFs for both locations, relevant airmet and SIGMET for the flight path, and pilot reports PIRP, then cross-referencing this information with current radar imagery and weather maps to assess the overall weather picture and potential hazards relative to the aircraft's capabilities and the flight plan. Option B. Relying on personal experience from previous flights in the general area and assuming the weather will be similar to past conditions. Option C. Reviewing the TAF for the departure airport and deciding to depart if the forecast indicates favorable conditions for the next 2 hours, without considering en route weather or the destination forecast. Option D. Checking only the METR for the departure airport to confirm it is currently clear, and then proceeding with the flight if the visibility appears adequate. The correct answer is A. Thoroughly reviewing METR for departure and destination, TAFs for both locations, relevant airmet and SIGMET for the flight path, and pilot reports, PIRE. Then cross-referencing this information with current radar imagery and weather maps to assess the overall weather picture and potential hazards relative to the aircraft's capabilities and the flight plan. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a pilot to synthesize multiple, potentially conflicting, weather reports and forecasts to make a critical go/no-go decision for a flight. The pilot must not only understand the information presented, but also interpret its implications for safety, considering the specific aircraft's capabilities and the intended flight path. The challenge lies in accurately assessing the risk posed by developing weather phenomena and making a timely, informed decision that prioritizes safety above all else, even if it means delaying or canceling the flight. Correct approach analysis. The correct approach involves a thorough review of all available weather products, including METR for current conditions, TAFs for terminal forecasts, airmet for en route hazards, and PIRP for pilot's reported conditions. The pilot must then cross-reference this information with weather maps and radar imagery to understand the broader meteorological picture and identify trends. Crucially, the pilot must consider how these weather elements, such as thunderstorms, icing conditions, and turbulence, might affect the specific aircraft's performance and safety margins, as outlined in the aircraft's pilot's operating handbook (PO) and relevant FAA regulations e.g. 14 CFR Part 91. This comprehensive evaluation allows for a risk-based decision that aligns with regulatory requirements for safe flight operations. Incorrect approaches analysis. Relying solely on a single weather report, such as only checking the METR for the departure airport, is a significant regulatory and ethical failure. This approach ignores the dynamic nature of weather and the potential for hazardous conditions to develop en route or at the destination, which are critical considerations for flight planning and safety. Making a decision based on a general feeling or past experience without consulting current, specific weather data is also a failure. This disregards the FAA's mandate for pilots to be knowledgeable of weather conditions and to exercise good judgment, as emphasized in 14 CFR 91. 103. Weather is constantly changing, and relying on outdated information or intuition is inherently unsafe. Choosing to depart based on a favorable forecast for the immediate departure time, but neglecting to assess the forecast for the entire duration of the flight, and at the destination, is another regulatory and ethical lapse. Flight planning requires consideration of the entire flight profile, including potential diversions, and failing to do so exposes the pilot and passengers to unacceptable risks. Professional reasoning. Professionals in aviation must adopt a systematic and thorough approach to weather assessment. This involves 1. Gathering all relevant weather information, METR, TAF, PIRP, airmet, SIGMET, radar, satellite imagery, and surface analysis charts. 2. Interpreting the data, understanding the implications of current and forecast weather for the intended flight path, aircraft performance, and pilot capabilities. 3. Risk assessment, evaluating the potential hazards and their likelihood. 4. Decision-making, making a go/no-go decision based on a comprehensive understanding of the risks and regulatory requirements, prioritizing safety. 5. Continuous monitoring, remaining aware of changing weather conditions throughout the flight. This structured approach ensures compliance with regulations like 14 CFR 91, 103, and upholds the ethical responsibility to operate aircraft safely.